Thank you, Sydney. So, hopefully I can, well, keep you awake while you are digesting the fabulous lunch you had outside. Today I want to talk about trends in systems and also about platform efficiency, because that's one of the major things that we are facing as a system integrator or an HPC vendor, you can say. And what you have seen over the last years is that a lot has changed. I mean, previously we had proprietary architectures and you had a proprietary software stack on top of that, and then you would run an application on that hardware and software stack, and you would mainly, because the hardware was locked, you would optimize the software. Nowadays, with all those different microprocessors, accelerators, GPUs, and co-processors, you have far more to choose from. So therefore, I think that the statement here on the screen is very valid, where the vice president of Microsoft Cloud Solutions said that if you want to tune more for inside the application, then you can also tune the hardware. So it's not only about the software anymore, but it is also about choosing the right hardware and making the right choices. Now, if you go back a little bit in history, and let's say from the 1970s up till the millennium, it was quite straightforward with the big mainframe vendors. You had a big memory bus here, and then attached to that bus you had the North Bridge, you had CPUs, you had a network interface, and then you had a memory controller and memory. So every CPU had the same view of the network and memory in the system, and then the system could grow in various ways. Then around 2005, we got the beginning of the multi-core era. So all of a sudden, CPUs had more than one processing unit. So not much changed except from inside the CPU, but we still had the controller, the bus where everybody had to hop onto, and the same view of memory and network. Then in 2007, with the Intel Nehalem architecture, all of a sudden the memory controller became on the CPU, which meant that the memory spaces were all of a sudden not uniformly across the machine, but they were separated. So cores on the left have a different view of the memory here than cores that are local to that memory. So the system is not fully balanced anymore, and therefore you have to work harder on the software level to get good performance. I mean, this is all common knowledge to most of you, I assume. In 2012, then, we had, with Intel Sandy Bridge, the PCIe controller, and all of a sudden, what you then saw was that also the view of the network was not uniform across all the cores, because the network card is a PCI card and has to be attached to one PCI controller. It can't be connected to two at a time. And what we then see in the future is more and more integration happening. So we have integrated network fabric, and we are now entering the whole system on a chip design. So it's becoming far more complicated, and therefore you can say also for the software far more challenging to get good performance. Talking about performance, we have two obvious laws that most of you know. We have Moore's law here on the left, where you can very clearly see the prediction from Gordon Moore that every 18 months you would get twice the number of transistors on a given die area. That is still happening. See, it's still a straight line going up all the way. But you see for the others, like the single thread performance, the processor frequency, the power consumption, you are hitting all kinds of upper limits. So we are not seeing an equal performance uplift compared to the number of transistors. So what does the number of transistors translate to nowadays? It is number of cores. And you can very clearly see that this has the same slope as the number of transistors. So more transistors means more cores. When you talk about more cores on a chip, then you talk about parallelization. and then we have that other law. We have Amdahl's law, and Amdahl said that already in 1968, he said, if you apply more cores or more processing units to a certain problem, then your speed up factor is being limited by the serial fraction in the code. So if you take this application or this example where I have an 80% parallel application and my wall clock time is 100 seconds to make it easy for us, then what you can see is that if I add more cores, then the parallel fraction halves, but the serial fraction stays the same. And if you would put this into a formula, then you would find out that for this application, I can never get a speed up factor of more than 5, right? So if I want to get better performance, then I have to work on my parallel fraction and to unlock more parallelism outside of the application. So you can say on this slide, Moore's law says more cores, but Amdahl says, well, you cannot use them efficiently. So from a system standpoint, we have too many cooks in the kitchen. So then, if you look at us as a system vendor, then customers expect from us that for every new server generation that it will have better performance or sustain a certain performance trajectory without massive increases in cost. Reliability should be better. It should be as dense as the predecessor, hopefully a bit denser, and it should be more reliable than before. If we want to build such a system and keeping the performance into account, then there is no single answer, but we can turn some knobs. And if you define performance, then you can define it in this way, where you have the frequency of a core on a processor socket times the number of cores on the socket times the number of sockets in the system, and then the capabilities per core on the socket. So the amount of operations or micro-ops that a core can do in a single clock cycle. These four are all hardware related. And the fifth one is your Amdahl's law factor, you can say. It's my efficiency, right? So how much of that performance potential can I effectively use? And that is being defined into software. If we now want to turn the knobs from what we have seen, then it was clear from that Amdahl, from that Moore's law slide, that the frequency will not improve, because otherwise we will run into reliability and all kinds of thermal issues. Though we see that number 2 is still true, we are getting more cores all the time because of Moore's law. Number 3 is an interesting one. You could increase the number of sockets, but then you would end up with a very big system. However, we are now seeing the first 8-socket standard x86 systems on the market. And I don't think that it is surprising, for example, that Intel is now natively supporting an 8-socket configuration with the Platinum Skylake-SP processor. Then the last one for the hardware is also very interesting, because what we have seen is that through the addition of specialized instructions, like the vector instructions and the FMAs and the accelerators, you can say that the capabilities per core have improved, right? So each core becomes more powerful in terms of what it can do in a single clock cycle. So that's definitely an area for growth, but it is again challenging because the developer or the user has to adapt the software in order to use those instructions. Number 5 can be optimized in various ways. You can start on the hardware level. So to improve the efficiency, you can say you could tune the BIOS of your system to your workload. You can tune the I/O layer and the process affinity in the operating system if you run multi-threaded or MPI. You can tune the MPI library itself. From the talk this morning by Professor Panda, we have seen all kinds of things that you can do with MPI in order to get better performance. So that's an example. And the last one to get good performance is to actually make changes in the application directly. But again, that is not very easy, and you really have to make your hands dirty. So you can say, if we then look at the Intel product development cycle, so the tick-tock model that we all know, you can see that they are constantly adding more capabilities to the processors, right? To the microarchitecture of the CPUs. So now with the Skylake, we are having AVX 512. And you can see that every, let's say, 2 to 3 years, you are getting a new instruction set added to the CPUs. But when you look at the application stack for high-performance computing, and I've here distinguished the major segments, you can see that the level of factorization, so the support for the special instructions, varies a lot. If you, for example, look at the CFD and computational structure mechanics applications, so the Fluents and the Nastrans and the Abacuses, etc., then what you see is that they do support very little factorization. And the reason for that is that the accuracy of their solvers is the most important thing to them. So if they change that to use new instructions, then also the accuracy can change. So therefore, they are way behind. Weather is different. Mainly they are open source, and also the nature of the simulation models is very suitable to factorization. Oil and gas is mixed. Yes, seismic, it's all about clock frequency, while reservoir simulation using stencil methods, it's very suited to factorization or special instructions. Chemistry using electronic structure methods, it's not really useful to use factorization because of the nature of the loops. But if you look at molecular mechanics, for example, or biology nowadays, I said not applicable, but now we also have integer factorization with AVX2 and AVX 512, then actually it is applicable. So you can see that it is mixed, and I will come to that later in a few examples. At the same time, what we're seeing, and this is a slide that I stole from the invited session at Supercomputing last year, where John McAlpin said that what you can see is that the system balance is really becoming an issue because CPUs are getting faster all the time, but at the same time, the data is becoming further and further away from the CPU. Even with the advantage in, for example, EDR and HDR InfiniBand with massive bandwidth, low latencies, from a CPU perspective, it is still very, very far away. And that is even more true for the latency than it is for the bandwidth, but it's an issue. So what can you do then on the system level? And I have yet chosen Intel here as an example. And what they are doing in order to fix those issues is that they are adding new tuning knobs to the CPUs, either to the BIOS level or on the instruction level, right? But at the same time, they are putting that responsibility in the hands of the users. If I want to test what the best operation mode is for my Skylake, then I have to make decisions on, am I going to run in a standard Snoop mode with 2 NUMA domains, or am I going to run in sub-NUMA cluster mode, where I have a cluster on a die, which gives me higher bandwidth and lower latency of some codes. And am I going to use AVX 512 with a different clock speed compared to standard AVX or SSE? It's all these choices have to be made by you as the user. Now, if you want to say something about performance, then what you can think of is the Roofline model. And the Roofline model, I think it was done in 2009 already by, I think it was Berkeley. And they wanted to say something about the arithmetic intensity and what it means to a CPU. Now, if you look at the major workloads in high-performance computing, then they all have a different kind of arithmetic intensity. And normally, the arithmetic intensity is being expressed as number of flops per byte. So if we have sparse methods like stencil operations or sparse linear algebra or lattice Boltzmann, then you need a lot of data movement for each byte. At the same time, at the other end, where you have dense linear algebra or particle methods, then you have very little data movement, but a lot of computation. So that is obviously very different performance from a CPU point of view. So you have work, or something that you can do, what we say flops. So this is a painting by Rembrandt of a girl writing something. And you can think of memory traffic, that's the other metric, so the number of bytes being transferred. And this is a copy, a book printing facility back in the old days, so where we are duplicating data. I mean, that is my view of memory generally. And then you have something like arithmetic intensity, which can be this, or, for example, if you go to an eye doctor, then it is the number of characters on a line, right? The more characters on a line, arithmetically intense it is. And this is what I found, and actually what I noticed, that you can find the word flop a lot of times on the lines, even on the last one. So for the people in the back, also here, you can see that there's still the word flop. So not a coincidence, I think, for us. So if we then look at a roofline model, then we have on the horizontal axis the arithmetic intensity, so the number of flops per byte, and here we have the number of gigaflops on the vertical axis. And you can calculate them because we can measure the amount of gigaflops that comes out of a system by running stream triad, for example, and we can set the maximum floating point peak by running linpack on a system. So if we say that the linpack is here at 1 teraflop, for example, out of a standard dual socket system, and we have our peak memory bandwidth. So if we do stream triad, for example, where we have to move 24 bytes and we do 3 operations, then we can also say how much gigaflops that is. So that is most likely being here. So when the performance of my application is here, then I say that it is memory bound. When it is here, so very arithmetically intense, then it is compute bound. And your aim is that you want to move up in a graph. So if you move from here to here with your performance, then you are, for example, making better use of caches, right? Because you can do more flops per byte. You have to move less data because it is already in the cache of the CPU. If you want to move up, then you can use a different kernel, and then you do all kinds of micro optimizations, as we call them, and then we get, well, closer to the peak performance of the CPU. Now, if we look at the latest Broadwell system, so the 2699, which had a peak performance of around 1.4 teraflop, measured on a Dell dual socket system. And we measured a peak memory bandwidth of 132 gigabytes per second. So this is my roofline, you can say. And you can see also that where I am about to reach my CPU utilization, that's around 8 flops per byte, right? If I can reach that, then I am getting close to the peak of the CPU in terms of arithmetic intensity and memory bandwidth. Now, if you then add the Intel Skylake, then you can very easily see what the Skylake brings me. And this is a logarithmic scale, I should add. The same for this one here. You can see because of the extra memory channels that we are getting more headroom here. You can also say that most likely the CPU is more forgiving because I can do more, I can move more bytes for the same number of flops. So therefore, most likely be able to get better performance. And very clearly, you can also see that due to AVX 512 and the extra units, that my floating point peak is also much higher. Now, if I add AMD to this chart, so the latest AMD Epyc, then you can see that it has been tuned very differently. It has massive memory bandwidth because we have 8 memory channels compared to 6. Massive stream number, almost 300 gigabytes per second, according to AMD. But the floating point peak for a dual socket system is quite low because an AMD system only has 228-bit units, and then it can do an FMA for each. But you see that the floating point peak is much lower. So I am probably getting good performance if I don't tune, but I have less headroom because my peak is lower, so I will be running out of steam earlier, right? So you can fairly clearly see what kind of behavior it would have. Then what about accelerators? This is interesting because you can see for example, the Knight's Landing 7250, so the Xeon Phi. You can run in very fast MCD RAM, or you can use standard DDR, and you can fairly clearly see that if you standard DDR has lower bandwidth, that I'm having less headroom to get good performance. And not coincidentally, I think that the slope of the P100 and the Xeon Phi with MCD RAM is about the same. So they are following the same trajectory, except for that the P100 has a higher floating point peak compared to the Xeon Phi. So if you can use MCD RAM or you can use a GPU, then most likely, because I have massive bandwidth, it should also give quite good performance already out of the box. So if I start with my Roofline and I have a Skylake CPU, then this is the picture that I showed you before. But this assumes AVX 512 and everything. But what if I can't use AVX 512 and fall back to AVX2, so 256-bit AVX instead of 512? You can see that my roof tops off earlier, right? Because I have the floating point performance. If I then, let's say I can't do the FMA, so I fall back to AVX because there's an opportunity to do a multiply add, then I am losing another factor of 2 of performance. So all of a sudden you see that I fall back from that 3.3 gigahertz all the way down to 700 something gigaflops. And then it can get worse because let's say that I can't do factorization, then I'm falling down to around 200 gigaflops peak. So you can very clearly see if you want to get good performance, then you have to work on your factorization. Otherwise, this is all that you can get. And it can even get worse when we talk about the roof, right? If I can't do instruction level parallelism in my code, then it's another factor of 2 lower. So you can say that you really have to work on the application side. Otherwise, you will run out of steam very, very quickly. So if I then add results, and this is what I measured on a Broadwell system, where we have that peak memory bandwidth and a certain floating point peak, you can say that I always lose something in my memory bandwidth because of the NUMA architecture. Because for each cache line, the core has to ask the other CPU whether it has a copy of that cache line as well, right? So this is giving me some overhead. If I then add data, then what I measured is that my stream triad is indeed utilizing the memory bandwidth that I have available completely. HPCG, which is MPI-based and hybrid OpenMP, but you can very well tune it to get rid of that NUMA factor. You can see that it is higher, right? So it is a little bit more arithmetically intense, and I can use more memory bandwidth because of the NUMA tuning that you can do. And then some other things that I measured, for example, OpenFOAM, it is bad, but this is to be expected, right? It's a sparse solver. CP2K, so molecular mechanics, is you're doing somewhat better. At the other end, we have HPL, obviously, which is, well, utilizing the whole floating point peak. So I am indeed maxing out here on the peak. But things like, for example, Chromax with its specialized kernel written in assembly is also doing quite well and is arithmetically very intense. So the last thing that I want to talk about is power consumption, very briefly, because we were talking about platform efficiency, and obviously power is very important. also when we go to exascale, then what we know is that we have lots of transistors due to Moore's law. But what we probably need is lower power per operation. Like I showed you, we have those operations that can work on a lot of data at the same time. That is probably the way forward if we look at how to be more efficient. So what I did was the following. I will firstly show you some measurements done by Intel. And what they did was they measured LINPACK performance and power consumption using various instruction sets. What you then can see here is that the power consumption for all of them is about the same. So that's flat, so it is utilizing the cores completely. For each kind of instruction, the Skylake processor has a different clock speed. So it is 3.1 gigahertz for SSE instructions, and for AVX it is from 2.8 all the way to 2.1 for the AVX 512. At the same time, I am getting more performance. But if you plot them differently, then what you can see is that we are losing efficiency here. You can say because of the SIMD, so where we do a single instruction on multiple data, we also have some kind of Amdahl's law thing on a chip. If I would do this linearly, then I should get the blue bar here, but it is stopping off earlier. So you can see that we are losing efficiency here, but at the same time, if we look at how much gigaflops per watt we can get out of the various instructions, then the AVX 512 is very clearly the best one. So I then looked at the NAS parallel benchmarks to see how they behave, and I looked at the top 6 of them, so where we have the conjugate gradient, the Multigrid method, both are memory intensive in various ways. Then we have the Fourier transformation, which is computationally intensive and also cache and memory intensive, and we have 3 solvers. And I ran them serially because that's the best way to look at the performance without having overhead. And let's say that I had 48 cores, then I was running 48 copies at the same time. And to start with the conjugate gradient, then what you can see here, and I said that it was memory latency, right? So it is HPCG-like. They were all running at the same frequency. So they were all running around 3.4 gigahertz, and this is time, by the way, and this is gigahertz. Then you see that they were all finished around the same time. So using special instructions for memory latency intensive applications doesn't help at all. Well, that's also to be expected. And you also see that the power consumption per socket is about the same for all 5 of them. It's all around 205 to 210 watts. Then for the Multigrid method, then what you then can see, and this is indeed workload time again, is that for this, the no factorization, so the worst, and the SSE, they are using the highest clock speed, but they also have the best performance because they are finished earlier than the other ones. But they are also consuming the most power, right? If you then compare the power consumption of these two with the AVX ones, then you can see that they are far more efficient in terms of amount of power used, but at the same time, you are sacrificing a bit of performance. For the block tridiagonal solver, then you can see that it is very beneficial to use AVX or SSE. So this is, AVX. You can see that they are much, much faster, and that AVX 512 is the most efficient with the lowest power consumption. And the same for the other solvers. You can then really see that it does make a difference, right? It is somewhat faster, but lower power consumption. I mean, that is very clearly the message. And it was totally not what I had expected, because I thought that the clock speed had to be lowered because of the complexity of those instructions, because last instructions do use a lot of transistors, and I had expected then higher power consumption. But actually, that was not completely true. So I have to ask Intel about the reason behind this. And for the other solvers, you can see that it is not always about better performance for the AVX, but it is definitely about lower power consumption. See, again, far lower power consumption than if I run scalar or with vector instructions. So that was my talk for now. So hope it was useful to get a bit of an insight of what we're looking at. And thank you.